So far we have only studied circuits that were pretty simple, so there was a voltage source and one resistor. But circuits with resistors come in all shapes and sizes, so in this video we're going to study how do we deal with more complicated situations. Resistors can be connected in series or in parallel. You probably saw this kind of arrangements when we were talking about capacitors. So this is pretty much the same thing. So when we have resistors in series like this, we would like to evaluate what is the equivalent resistance of this kind of system. When they're in series, that's pretty simple. The equivalent resistance is just the sum of all of three. This is pretty intuitive, so if this is one resistor and then we have another one here and third one here, so this has length L, so if we add all three one after another, the length becomes 3L, which means that the resistance increases when this L increases. So in series, we just add them all together. When the resistors are in parallel, like here, then the situation is a little bit more complicated, and the equivalent resistance can be calculated from this kind of relation. So 1 over R equivalent is 1 over R1 plus 1 over R2 plus 1 over R3, and etc. if we have more of these resistors. So basically, to calculate the equivalent, you have to plug in values for each of these and then take the reciprocal of the result. We saw the same kind of formula when we had capacitors. And in that case, the trick was if we have only two of them in parallel, which is quite a common occurrence, then the R equivalent was simply the product of the two divided by the sum of the two. A lot of times this is very handy and a quick way to evaluate when there are only two in parallel. This is a pretty simple concept, but I'd like to give you a word of caution. You might remember earlier when we were talking about capacitors. So if we had capacitors in series, C1, C2, and if that's C3, then the equivalent capacitance was found from this relationship. 1 over C equivalent 1 over C1 plus 1 over C2 plus 1 over C3. And then if we had capacitors in parallel, C3, C2, C1, in that case the equivalent capacitance was just the sum of them all. So as you can see, these situations are exactly the opposite for resistors and capacitors. For resistors, the easy one is when they're in series, but if capacitors are in series, it's the more complicated one. And for capacitors, the easy one to calculate is when they are all in parallel, whereas the parallel configuration for resistors is the hard one. So you have to be careful that you don't assume that whenever stuff is in series, you calculate them in the easy way. No. Easy way only when resistors are in series or if capacitors are in parallel. As always, we have a couple of exercises. So in the first one, we have a 10 ohm and a 15 ohm resistor. And what is the smallest and largest equivalent resistance that you can make with these two resistors? So we have two options. We can connect them. That's the European way. Let's stick to the American notation. So there's a resistor. That's 10 ohms. And then we have another one in series. That's 15 ohms. The R equivalent in this case is just the sum of the two, 10 ohms plus 15 ohms, which is 25 ohms. However, if we connect them in parallel, so here we have 10 ohms and 15 ohms. We can use the simple trick calculating when they are in parallel. So then the R equivalent would be the product of the two, 10 times or 10 ohms times 15 ohms divided by the sum of the two, 10 ohms plus 15 ohms. So this is 150 ohms squared divided by 25 ohms. So these cancel and we get 6 ohms. So the smallest one is 6 ohms and the largest is 25. And as you can see, whenever we connect resistors in parallel, the total resistance is smaller than any one individual resistance. And this makes sense. When we have two parallel lines, there's going to be more cross-sectional area for the electrons to flow, so they will see less resistance as a whole. Here we have a little bit more complicated case. So we are supposed to find the equivalent resistance for the whole circuit. And we'll start solving this piece by piece. So we start from the middle. What is the equivalent of these two? So it's 8 and 4. So that would be 8 times 4 divided by 8 plus 4, which is 32 divided by 12. That gives 2.7 ohms. So this one can be replaced by something that is 2.7 ohms, one 2.7 ohm resistor. So in that case, our circuit would look something like this. 10 ohms there, then this other branch 6 ohms. Here we had 2.7 ohms, and then the rest is the same, so 5 ohms, and here we had 0.5 ohms and the battery. Now next, these two add up into 8.7. They're in series. We just add them together. Another question is, what is the equivalent resistance of this whole chunk? So again, it's this one in parallel with 8.7. So product of the two, 10 ohms times 8.7 divided by the sum of the two, 10 plus 8.7 ohms. So, and this gives in fact 4.65 ohms. So now this big chunk reduces into one resistor, and in total we have the battery here, .5 here. This whole thing was replaced by one that is 4.65 ohms. And then we have this 5 ohm resistor here. And now the R equivalent of these three, which is same as the R total, is just the sum of all of them. So 0.5 ohms plus 4.65 ohms plus 5 ohms. So that gives us 9.65 plus 3, that's 10.15 ohms. So remember the trick, when two are in parallel, it's the product of the two divided by sum of the two. Like I mentioned in the case with capacitors, this result cannot be generalized when there's 3 or more resistors in parallel. This only applies when there's 2 of them.